Pleasure to be here. Do you mind if I turn off the lights? Or is it okay with the camera? All right. Perfect. Yeah, that's good. All right. So I will be talking to you today about soap bubbles and sort of their mathematical formulation. So the aim of this talk is to prove the isoperimetric inequality, which in the Euclidean setting states that, well, basically the volume of a set is controlled by the perimeter of a set. So quantitatively speaking, it says the following. So let me just write that up. So if you have any set E, and the absolute value of E will be its volume. So that's just a notation that's sort of standard for that. So if you have any set E, then this estimate holds. And what this tells you is that, okay, B1 is the ball centered at the origin of radius 1. So in R2 would be like this guy with radius 1. And so this is just a constant. N is the dimension. So think of n equals 3, three-dimensional space. So in three-dimensional space, if you ask the following question, okay, I'm gonna fix a number, let's say like 5, and then you look at all subsets of three-dimensional Euclidean space with volume equal to 5. And then you ask, okay, among these guys, which one minimizes the perimeter? Okay, so that's the isoperimetric sort of problem. And the answer is, any guesses? Sphere. Okay, so the ball, right? Because in some sense you can compress a lot of stuff and then just get a little bit as far as perimeter. And that's what, quantitatively speaking, if you want to prove that sort of maybe obvious statement mathematically, then you have to prove an inequality like this. So that if you fix that number, 5, and then so that the measure of E is just fixed, it's 5, then the perimeter of any set E with volume equal to 5 will be greater or equal to this number. Remember, this is a 5 to the 3 minus 1 over 3. And this turns out to be equal to if, let's say, the measure of E is 5. This is going to be the perimeter of the ball of radius r, so that the measure of the ball of radius r is equal to 5. So you can compute what r has to be to make this happen. Okay, so this is just sort of an example that illustrates the point. So the point is that under a fixed volume constraint, you cannot do better as far as minimizing the perimeter than the ball. So the ball is the optimal guy in that sense. So what we want to do is we want to prove this estimate. And by the way, if you see a kid blow a soap bubble, the soap bubble, of course, is spherical. And you might ask, maybe there is a connection. Well, the connection is that, in some sense, nature doesn't want to work very much, but it wants to be very efficient. So instead of when you blow the oxygen into the bubble, then the molecules of the soap film will adjust themselves so that they produce the least sort of surface area. And that configuration is indeed the sphere. So that, in some sense, nature is extremely efficient in creating things. So hence, when you blow that soap film, it turns out to be a bubble. Okay, and what we want to do is we want to apply this theory called optimal transport theory to address this problem. So the proof of this inequality will be an application of what I'm going to talk about right now. Okay, so what's this Monge transport problem? Okay, so basically Monge was this French mathematician living in like the 18th century. And he was actually hired by Napoleon to do some military work. And during this time, he encountered the following problem. So suppose you have a pile of sand, and you have a hole. Okay? So basically what you want to do is you want to move the sand into the hole. Suppose that the volume of the sand is equal to the volume of the hole, so that everything fits nicely. Okay? So the question is, how do you move the sand into the hole so that you minimize the cost of moving sand into the hole? Because when you move a little sand grain X into a little point Y here in the hole, well, you have to pay. You have to pay to move little x into little y. So what you want to do is, you want to, in some sense, minimize the cost. And so the model is as follows. So basically, you're measuring, in some sense, the sand will be, in math language, will be like a measure. So a measure is just a thing that takes in as input a set, and it spits out a volume. Okay? So that's, for the purpose of this talk, just think of that as a measure. So it's just a way of understanding the volume of something, of a set. Okay, so you have the sand pile here, and then you need a cost function, c of x comma y, which tells you the cost of moving little point x to little point y. And basically what you want to do is you want to sum up over all the sand grains that you're moving, and you're measuring them with, let's say, some measure mu plus. Okay, just think of this as dx, if you haven't seen stuff like this before. And let's say the sand is E. So we'll denote the sand as E. And then the hole is K. Okay, so this is the cost of moving little x to little y, summed up over all possible x's. And you want to minimize this. So you want to take an infimum over all. So first of all, we need a function t that maps little x to little y. So y will just be t of x. And then we want to take an infimum over all t such that, okay, let me just write it down what it is, and I'll explain it. So that t pushes the measure mu onto the measure mu plus onto the measure mu minus. Okay, and what does this mean? This, by definition, just means that mu minus of f is equal to mu plus t inverse of f. Okay, so it's very easy to picture. And by the way, I'm going to put the slides on my website, so if you can refer to them later, if you wish to do so. You know. So anyway, so you have a set f here, and then you pull it back, so the pre-image is like somewhere here. So t inverse of f. And all we ask here is that the infinitesimal volume is preserved. Okay? So that when you pull back a little region here, over here, measured with respect to mu plus, it's got the same volume. Okay? So that's what we ask. Good. So this is the Monge, this is called the Monge problem. So, i.e., does there exist a t that minimizes the cost of transport? Okay? So this is a function of your measures. So if your measures are weird, like Dirac masses, then no such thing can even exist. Like you're taking an infimum over an empty set, which is always a bad thing, right? So to make sure that, to give sense to this problem, you sort of have to make some assumptions on the measures mu plus and mu minus, which I'm not going to get into. Just if they're, for example, absolutely continuous with respect to Lebesgue measure, which means that just think if they're just sort of volume measures, you know, when you think of the volume of this box here, you know, and you're computing it with the measure, it really turns out to be the volume, the normal thing that we think of. Maybe scaled a little bit, but more or less the volume. So if the measures are nice, kind of like the volume measure, the standard one, then this thing is well posed. Okay, so this is what I was talking about here. So the hole has the same mass or volume as the sand. That's what this says. The move is a one-to-one Borel map that goes from E into K, that goes from the sand into the hole. And then we require that infinitesimal volumes are preserved. So that's what that means, that T pushes mu plus onto mu minus. And we want to minimize the cost. Okay, so that's what I wrote up there. Okay, good. So so here is a theorem that in some sense, gives us some information about this problem. So let me point out that, so Monge posed this problem in 1781. So until 1940s, we made very little progress on that as a mathematical community. And then in 1942, Leonid Kantorovich, a Russian mathematician, figured out that you can actually rephrase this problem in terms of a different problem. So instead of taking an infimum over these maps, you can actually take an infimum over product measures. So that was his idea. So you basically, okay, it looks like this. So you leave y, you don't assume that y comes from some map, but then instead of d mu plus, you put d gamma of x comma y, where gamma is just the measure in two variables. Think of it like dx dy. And okay, and you're taking infimum over gammas in some set, which I'm not going to define. But basically, what Kantorovich did, he replaced this problem with this problem. And for this problem, you can use compactness ideas. Okay? So here, basically that, like in R, every bounded sequence of real numbers has a convergent subsequence. Well, it's sort of the same thing in this setting, because every bounded sequence of measures has a convergent subsequence. But then you have to specify the topology in which these things live and so forth. So I'm not going to get into that. But that was the method of attack in 1942, proposed by Kantorovich. He, by the way, won the Nobel Prize in 1975 for work related to this. And he was actually studying how to place cars like on a lake with ice so that like the ice doesn't break. And this was kind of important in World War II for them. So this stuff had like practical applications. But then later, mathematician. So he was sort of he was a mathematician and an economist. But we were trying to understand. Okay, so then we know that with this you can produce a gamma that minimizes the cost, and then you have to prove that gamma comes from a map T. Okay, and this was done using a theory that sort of he developed. But then little was known about that T, except that it was the gradient of a convex function. And like uniqueness and stuff those are pretty difficult issues to deal with. But anyway, so here's a theorem that says that if you have a strictly convex cost function, okay, for the cost function, just always think of it as a quadratic. That's the nicest cost function you can imagine. Just think of it like this, okay? So that's a cost function. Then the Monge problem is well posed. Excuse me, and up to a set of measure 0, the optimal transport map is actually unique. And it's also the gradient of something convex. And you'll see how this property will help us prove the isoperimetric inequality. Okay, so in this case, this was done by Brenier in 1987. He's a French mathematician, and actually met him this past summer. He's a really nice guy. And the general case was discovered independently by Gangbo McCann and our very own Luis Caffarelli, okay, in about 96. So we've already addressed the question of why soap bubbles are spherical. So let's try to relate the Monge problem to the isoperimetric inequality. Okay, so suppose that E is just a set. Let's assume that the boundary is smooth, meaning that it looks kind of like this. It doesn't have sharp corners, although this is not really an issue. But for the purpose of this talk, let's just assume that it's got a smooth boundary. Then we can calculate its surface measure. So okay, so if you're a ball, then it's just 4 pi r squared. So then this is the theorem that we're trying to prove. That's the isoperimetric inequality, the Euclidean case. And let's prove it, because we have all the tools. Thanks to that theorem that told us that the map is the gradient of a potential. Okay, so what you want to do is you want to fix the mass first. So okay, B is going to be the unit ball. And so I claim that we can assume without loss of generality that the measure of E so the volume of E, whenever I say measure, I might say it and not realize it, but I always think volume. So the measure of E is equal to the measure of the unit ball. Okay, why can we do that? Well, that just comes from the scaling and variance of this quantity and this quantity. So assume, so here's the proof. So assume the measure of E is not equal to the measure of B1. So then find alpha, some positive number, so that this holds, right? We can do that because this is equal to alpha to the n. So just think of three-dimensional space if you're uncomfortable with n. So you can prove that if you dilate a set by some number, some positive number alpha, then and you compute the measure of alpha times that set, then it's actually equal to that constant to the power of the dimension times the original measure. So surely we can find alpha so that this statement holds, right? Alpha is just the volume of B1 over the volume of E to the 1 over n. And then just plug it in. So we assume that the statement holds when the measure of E is equal to the measure of B1. So we want to prove that in general, it then holds as well. So since alpha E, this new set, has the same mass as B1, and we assume that the inequality is true, then we get that the inequality is true with alpha E. But the perimeter scales like alpha to the n-1 PE. And that's, OK, if you believe this, then it shouldn't be too hard to convince you that this is true, because in some sense the surface is n-1 dimensional. So think of R3, you've got the ball, it's 3-dimensional, but its surface, the sphere, is 2-dimensional, right? So, OK, this is not too hard to believe. And here the scaling just works out, because this is just, this part here is just alpha to the n when you pull it out, but then you get 1 over n, and then n-1. So alpha to the n-1 times the measure of E. And so the alpha n-1s cancel. And you prove the statement with the general E that did not have the same mass as the ball for this one. Okay, so we can reduce to the case where we assume that the measure of the sets that we care about have the same mass as the unit ball. Okay, so now what we want to do is we want to apply the Monge problem. Well, the Monge problem takes as input 2 measures. Okay, so 2 different ways of measuring volumes. So what we're going to do is we're going to consider really nice measures. Excuse me. So we're going to consider these uniform probability measures. So, OK, actually, I'm not going to say anything about that. We're just going to take these measures. They're very nice. And they're candidate measures for the theorem that we wrote, that was done by Caffarelli, McCann, Gangbo, Brenier. So, OK, so here, so I should probably write it. OK, maybe I'll write it down. So, mu plus. So what we want to do is, OK, we have the set E. We want to map it into the ball, right? And what we want to do is we want to use the optimal map given by Monge's minimization problem to map this set into the unit ball. And we're going to extract some information from there. OK? So for that, we need 2 measures which kind of model the sets E and B. And these are the appropriate measures. So mu plus, if you're a set F here, then mu plus has what volume with respect to this set? So the sets are disjoint, right? So when you do F intersected E, you get the empty set. So it's 0. So mu plus only targets sets that have a non-trivial intersection with E, right? And that sort of models that we're just moving the sand out of E. Like sort of E, think of E as the sand and B as the hole. Okay, so mu minus, again, it just targets sets that have a non-trivial intersection with the ball. And okay, and so we want to minimize the transportation cost between E and B. So we know that there exists a map T so that T pushes mu plus onto mu minus, and it minimizes the transportation cost. As far as minimizing the transportation cost, that will be embedded in the fact that it's the gradient of a potential, but I'll get to that. So right now what's important is that we've got this relation, and that such a T exists. Okay, since T is equal to the gradient of a convex function, we actually know that if we take a derivative, okay, so phi is a function, it's a real valued function. The gradient of that is a vector. So then when we take another derivative of t, that's a matrix, right? So dt is like d squared phi. So it's the Hessian of phi. So phi is just a function. D squared of phi is the matrix. And because the function is convex, the determinant of this matrix is actually greater or equal to 0. Okay? Just think of, I don't know. Okay, how about f of x equals x squared? F double prime of x is equal to 2, which is positive. Right? So so in just one variable, the Hessian is just the second derivative. The determinant of a number is just the number. And you see if it's convex, so if it looks like this, then the determinant is, in this case, positive. But in higher dimensions, you can prove that that it's non-negative if the function is convex. Okay, so now the proof is very simple from here. We have all the tools. So basically, okay, so let's do this. So first, we need to compute the determinant of this Hessian. Okay, so how to do that? So for that, we're going to use this. So take f to be any subset of the ball of radius 1. I guess I'm dropping the okay. And mu minus of f is equal to mu plus t inverse of f. Our measures are these guys. So let's just write that in here. So this means that f intersected with E over the mass of E is equal to T inverse of F intersected with, B. Yeah, okay, okay. I was supposed to use this one. Okay. So T inverse of F intersected E over the mass of E. We assume that the measure of E is equal to the measure of the ball, right? That was that first scaling argument that we did. So we can just get rid of this. Okay, so but now, because F is somewhere here. So because F is a subset of B, the pullback of that will be in E. So T inverse of F is in E. So we can get rid of E. And F is a subset of B. So F intersected B is just F, right? We're all on the same page? So we just get this relation. So the volume of F is equal to the volume of the pullback under T. Good. So now we're just going to compute this volume. So this volume is the integral. So we compute volumes by doing integrals. So this is just dy over f, right? And here's like a 1. So you count each point in f, and that's how you compute the volume. And now what we're going to do is we're going to say, OK, let y be equal to t of x. We're going to do a change of variable. So from calculus, if t is, let's say, smooth, then you know that dy is given by, anybody remember the formula? But OK, but something with the determinant, right? There was a determinant there, right? Like a Jacobian thing. Remember Jacobians? OK, anyway, so I'll put it up, you'll remember it. So the absolute value of the determinant of grad t of x dx. So we can, OK, so remember it's like the Jacobian of the transformation times dx. Anyway, OK, that's Calc 3. And so we just plug that in here. So, so y goes through f. So x goes through t inverse of f, right? And then dy is just given by this expression. But now we use the fact that the determinant of the Hessian of a convex function is non-negative. So we can get rid of the absolute values because t is actually, so t is the gradient of a convex function. So when you take another derivative, it's the Hessian. So grad t is the Hessian of phi. But the determinant of the Hessian of a convex function is non-negative. So as remember this example. So we can get rid of the absolute values. So we just put determinant of, yeah, just grad t. OK. X dx. All right. So now, OK. So we're taking the determinant of a matrix. And the determinant of the matrix is the product of its what? The eigenvalues. OK, so if the matrix is like diagonal, then it's just the product of diagonal. Yeah, so OK, so remember that the determinant of a matrix is equal to the product of its eigenvalues, right? So that's linear algebra. So we are going to use a little bit of linear algebra here. So let me continue up here. So this is equal to the integral of t inverse of f of the product of the, let me just call them lambda I. They depend on the point x. And OK, actually, let's forget that part for now. We actually just need this. So we did the change of variable. So just trace the equality. So the measure of t inverse of f is just integral of dx t inverse of f. Trace it from right to left. So this guy is equal to 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 this guy. So overall, let me put that up here. We get integral determinant grad t dx. OK, but now, how did we pick f? F was any subset of B. So in particular, t inverse of f is actually any subset of E because t is 1 to 1. So you can actually write any subset of E. So for any, let's say, A subset of E, you can write A is equal to t inverse t of f, t of A. So actually, since f was arbitrary, A is also arbitrary. You can recover any, pick any A, and then it's going to have the form t inverse of something. So we can actually appraise this t inverse of f with just A. A is for any A subset of E. But if the integral of two things over any set are the same, what should that sort of intuitively tell you about those two things? The two things being this guy and then 1. They're sort of equal, right? I mean, come on, you're like, you can pick any set. Like if they're not equal, then you can find the small set on which they're not equal. So then you violate this, right? So, okay, so that's reasonable, right? So then the first thing that I wrote up there, by change of variables, the determinant of the Hessian is 1. Okay, that follows from this change of variables. That's what I meant by that, okay? So that's hopefully believable. And now you just, we just do a computation. And it's a really cool computation. Okay, so just let's just recover in simple terms sort of what that means over there. So, okay, so you have, so since the measure of B is equal to the measure of E, you can add the exponents, right? 1 over n plus 1 minus 1 over n. So it's just 1. So you get n times the measure of E is equal to, well, n times dx as x runs through E. But now the determinant is 1 by that change of variable we did. So this is just, so we can just write this as n integral over E of 1, which is the determinant of grad t. Remember, this is a matrix. And for fun, we're going to put a 1 over n here. 1 over n, doesn't matter, dx. OK, but now, the determinant of a matrix is equal to the product of its eigenvalues. Okay, and the eigenvalues are actually non-negative because the matrix is non-negative definite. So now what we're going to do is we're going to use the AMGM inequality. So so that just states that the product of a bunch of numbers, non-negative numbers, is less than or equal to the average of them. Okay, so that's AMGM. So we're going to use that here to say that this is less than or equal to, okay, n stays as it is, E, and then the sum of the lambda I of x over n dx. The n's cancel. And now lambda i's, they're the eigenvalues of which matrix? Let's write it up here. So it's something like T1, x1, T1, x2, xn. So this is the matrix grad T. And but the sum of the eigenvalues of a matrix is equal to what? Starts with a TRA. The trace of the matrix, right? So it's this guy. But look, that's just the divergence of T, right? T is a vector. Okay, let me put that here. So T is like T1, T2, T3, dot, 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 Tn. So the gradient, like grad dot T is the divergence. So that's just like partial x1, comma partial x2, dot, 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 partial xn, inner product with T. But that's just equal to this guy, right? Since these are the eigenvalues of this matrix, and because the sum of the eigenvalues is equal to the trace of the matrix, and because the trace is equal to the divergence of the T, we can write that this is actually equal to integral over E of divergence of T. Okay? Cool. And now, now what? Okay, now we just use the divergence theorem, right? So we just say that, well, this is equal to the integral over the boundary of E of T dotted with the normal to the boundary. And this is, okay, the measure is not like dx, it's the Hausdorff measure, but let's just call it, I don't know, ds. It's the surface measure. Okay? But now we're basically done, right? Because this is, so A dot B is less than or equal to mod A mod B, because there's a cosine, but that's less than or equal to 1. So T dot nu E is actually less than or equal to the modulus of T, because the unit normal has norm 1, and then ds. But now mod T is what? Remember, T, now we use the optimal transport thing. So T goes from the sand into the hole, but what's the hole for us? So, so T goes from E into what? K, which was B1. The ball of radius 1, right? So the modulus of T can be no larger than what? 1, right? Because it maps into, like, T of X is a subset of the unit ball. It's somewhere here. It can't be more than 1. So the modulus of T is less than or equal to just 1. But wait, this is just 1 ds? But that's just, okay, integral. So remember here, okay, where did I introduce it? The perimeter of E was defined to be the integral of ds over the boundary of E, right? So then this is just equal to the perimeter of E. Okay, so this proves it. So so what did we use from optimal transport theory? Well, we used that a map T exists. It's 1-to-1. It's the gradient of a potential. And that gives you so much information about the structure of it and its derivative, i.e. its Hessian. The Hessian of the convex function, of which it is a gradient. So we totally exploited that in here. And the cool thing about this proof is that it's short, and it gives you the equality case like this, okay? Because the only inequality we really used, more or less, like the only non-trivial one we really used is the AMGM here. But there's equality in AMGM if and only if the numbers are all constants. And in this case, because the determinant is 1, the constant will have to be 1. But then you can reconstruct T through its eigenvalues, okay? And actually, it'll tell you that T is just basically the identity, so that the E that you started with was really the ball. So if you have equality in this inequality, then you're the ball. Okay, so now we want to study sort of the stability of it. I have 1 hour or 50 minutes?
About an hour.
Okay, so 15 more minutes, 16 minutes, okay. So basically, what's the stability thing? First of all, any questions about the proof? I should probably comment that the original, if you just take your favorite, I don't know, geometry book or something and try to find a proof for this inequality, you'll see that, I mean, it's not that easy. And actually, the general inequality, I mean, sort of one way of proving the isoperimetric inequality, historically speaking, is this thing called Steiner symmetrization. And that's, I mean, you'll see if you look into it, it's not very sort of simple to, certainly not as short as this proof. So in some sense, I mean, I think this proof is more or less optimal. But of course, it builds on that theorem that we stated initially, which is very deep and very difficult. So in some sense, I mean, yeah, the proof of this is simple, but the machinery used to develop the proof of that theorem that we used extensively is sort of hard. So yeah, just a note on that.
Is there a 1
yeah.
over n on your geometric mean?
Where?
On the geometric mean there. The geometric mean, the AMGM or up top. To the roof.
Yeah, thanks. Yeah, thank you.
I thought I was smoking crack for a second.
No, I mean, we use that here.
Oh yeah.
Yeah, no. Okay, thanks. So now what we want to do is we want to study stability issues. So remember, what we proved was so for any set E, this statement is true. That's what we prove, right? So now what we want to do is define delta E. So define delta to be a functional on sets. So its domain are sets. So it takes in a set, and then it spits out a number. Okay? So in this case, which number is it going to spit out? It's going to spit out, what we're going to do is, we're going to take this inequality, we're going to divide by left-hand side. Okay? So this over left-hand side is just greater or equal to 1, and then we're going to subtract 1. So we know that if we make this definition, then delta V is non-negative by the isoperimetric inequality, right? So that's what this says. So because delta's, so delta in some sense, if delta is really small, geometrically, what does that tell us about our set E? It tells us something, right? But what does it tell us? That it's sort of stable with respect to what? Yeah, no, okay, it's stable with respect to this inequality, right? But stable, what do you mean by stable? Stable is kind of like this vague thing that's thrown around a lot. But in this sense, you're absolutely right. It's stable with respect to this inequality. So that the set that achieves equality in this inequality we have seen as just the ball. So if somehow delta, if the deviation from the optimal perimeter is very small, if delta is really small, then in some sense E and the ball should be like what? Kind of like almost twins, right? They shouldn't, I mean, E shouldn't be too far away from the ball, right? So that's kind of natural, right? Like so the ball minimizes the perimeter under a fixed volume constraint, and if you're like the perimeter plus 1 over a million, if you're the optimal perimeter plus 1 over a millionth, of just 1 over a million, plus little epsilon, then in some sense you shouldn't be too far away geometrically from the actual set, right? The way to measure this sort of geometric deviation is the asymmetry index. So by the way, delta is called the isoperimetric deficit. The asymmetry index basically tells you, geometrically speaking, how far do you deviate from the set. Okay, so it's defined in terms of this big infimum thing, but the way you should think of it is just the following. So, okay, so just to fix notation, A symmetric difference B, you have two sets A and B, so A and B. The symmetric difference is a set, okay, and it's everything outside of the intersection. So in the picture here, it's yellow. So if you prove that everything outside of the intersection is very small, like here, let's say, everything outside of the intersection is small, then you're somehow forcing the sets to be more and more the same, right? So that's how we measure sort of this geometric deviation from the optimal guy. And you can translate this, so we're taking basically an infimum over just translates of the optimal set in the isoperimetric inequality. So the asymmetry index, alpha of E, just measures geometrically how far are you away from being the optimal guy. I mean physically, geometrically as in physically. So delta is a geometric quantity, but that's more like perimeter. It's more like how far do you deviate from being the optimal perimeter in the isoperimetric inequality. The asymmetry index just tells you like, okay, seriously, geometrically speaking, how far are you from being the ball? And it turns out that there is a relation between these two things. Yes?
So is that asymmetry, I mean, are you basically trying all the different balls and comparing them to your set and finding the closest one?
Yeah, exactly. Yeah. So yeah, exactly. So that saves time writing down that okay, measure of E is the measure of B, and then you could get rid of this R to the end thing. But you have a set E, and then you're trying this ball. So if he's here, they're very far apart. So you want to translate him here, but then he's too small. So you want to make this guy bigger. Try the same thing, move him here. But then this guy is too big, so you want to make it a little bit smaller, and then maybe this is the guy. So that's what the infimum is taken over. So you're just scaling to make it bigger or smaller so that like sort of approximates E in like the best possible way. Yeah, good. So okay, so what would you expect? I mean, there should be a correlation between like the asymmetry index and the isoperimetric deficit, right? I mean, in some sense, if you're very, I mean, sort of, you know, what she said before with the stability thing. So if delta is very small, right, then in some sense you're not too far away from being like the optimal guy in the context of the isoperimetric inequality. But if that's the case, I mean, come on, physically you shouldn't be too far away from being the ball, right? So you can actually do this sort of compactness argument, which is not too difficult, to prove that discontinuity. So i.e., as delta goes to 0, alpha E goes to 0. So that, you know, if you're getting better and better in terms of optimal perimeter, you're actually converging to the ball. What we want to do now is actually the stability problem. So it's a very general sort of problem. It states, OK, can you find an explicit estimate? So we already know that as delta goes to 0, alpha goes to 0. But the stability estimate wants constants C and beta so that you have exact control on the decay. So you know exactly how fast alpha goes to 0 as delta goes to 0. Okay, so compactness arguments give us the continuity property. This is much better. It gives us like an explicit rate of how alpha goes to 0 as delta goes to 0. So now the problem is find beta and C. Okay? So that's the stability problem. All right, so it turns out that that you can actually prove that you can take beta to be 1/2, and C is just a constant, which depending on the paper that you're reading, you can explicitly compute, or it's given by this abstract compactness argument. So there exists a constant such as blah blah blah, but then you know you can't really find it. So depending on these two sort of different scheme of, and we actually don't really, I mean, if you want to do numerics, then of course you need some like upper bound on the constant at least. But I mean any constant is good. I mean, as long as there exists a constant, I mean that's like a good thing. So just some remarks. The case n equals 2 was done in 1924 by Bernstein and Bonnison. Then in 1924 and 1989, that's the first general result. Higher dimensions. So that was just n equals 2. And so in like the 90s, there were a lot of contributions from Hall, Hyman, and Weizmann. And they proved that you can take beta to be actually 1/4. So the theorem that that theorem above is the state of the art. That's like what we have as of today. That's like the best thing we have. So this is just sort of tracing its evolution. So in the 90s, Hall, they were able to get 1/4. That was good. But then they were like, you know, we only care for delta small. So the bigger the exponent, the better. Right? We only care for delta like for sure less than 1. So so Hall conjectured that I don't think, you know, he conjectured, he said, you know what, I don't think 1/4 is the best constant that you can get. He said, I think 1/2 is. And actually this was recently confirmed in an analyst paper from 2008 by Fusco, Maggi, and Pratelli. And actually Francesco Maggi is visiting here. He's a friend of my advisors and a collaborator. And yeah, so they proved that you can actually get you can get beta equal to 1/2, thereby confirming Hall's conjecture. Now, what are generalizations to this? Okay. So the way we defined the perimeter was just, okay, you take the set, and then you just take the surface measure of the set, right? That's the way we define perimeter. It turns out that this is not a good enough definition of perimeter from, let's say, the point of view of crystallography. So okay, so the perimeter we used was the isotropic perimeter. So there is this thing called the anisotropic perimeter, which I will denote as PK. And okay, I mean I can write down the formula, but it's kind of complicated, and you need kind of, you know, I don't really want to define these things at this point. But basically, I should probably write it. Okay. Because it's like this abstract thing if I don't. So PKE is equal to, okay, just bear with me. So this quantity, so you fix, this is with respect to some k. This is sort of a norm. You're basically integrating, instead of integrating one, you're integrating something. Just think of this thing as like a function acting on the unit normals. So you have your set, and then you have a bunch of normals. And in the Euclidean case, each normal has length 1. In this case, the normals could have different lengths. They can even be negative. So I'm not really going to define what, well, I should probably define this, but then dot x, as x runs through k, and k is some convex set. So you fix a convex set that's open and bounded, and then the perimeter, the anisotropic perimeter with respect to k, is given by this integral. Okay? So you're integrating just the surface measure over the boundary of E. You look at the normals, but then you kind of weight the normal so that this could be like different numbers depending on what it is. So that has applications in crystallography. And okay, so then you can actually ask, okay, can you prove an inequality of this form with this anisotropic perimeter? And it turns out that yes, you can do that. And Dingas showed that you can actually do this for like smooth sets, I think. And I mean, it holds for much more general sets. I mean, they could have like cusps. Like any set of finite perimeter works. But anyway, so this is the estimate. So the ball was the optimal guy for the Euclidean case. So in this formulation, k will be the optimal guy. So think of, so you're starting with any convex set, say something like this, and somehow you can tweak the perimeter so that like k becomes the analog of the ball in the Euclidean case. Okay? So k is the optimal guy. K is the guy that we like. You can pose this, then you can define delta sub k, because now it depends on the convex set k. This is delta sub b, where b is the ball, the Euclidean ball. Then you can ask the same stability problem now in this context, but now everything depends on k. Okay? So that's sort of, so in 2005, let's see, Esposito, Fusco, and Trombetti, they proved that you can take beta to be this quantity depending on the dimension. But then there was still that conjecture, okay, but somehow 1/2 should still be optimal. Like, we want 1/2. And this was done by Figali, Maggi, and Pratelli, and Figali is actually, Alessio Figali, he's here at Texas, he's my advisor. So they obtained this 1/2 rate recently, which of course recovers the 2008 paper by Fusco, Maggi, and Pratelli, because you just take k to be the ball. Okay? So as a corollary of their theorem, you get the other theorem. And now so the 2008 result was actually done using symmetrization techniques. So sort of the contribution here was that you can explicitly compute the constant, so this constant c, and it doesn't depend on k, just depends on the dimension, which is interesting. Even in the anisotropic case, it doesn't depend on k. And you can explicitly compute what the constant is, whereas in the 2008 paper, they relied on some compactness argument, so they were able to prove, okay, there exists a constant so that this holds. But then quantitatively speaking, you can't really compute it. Okay, so then sort of my problem was sort of so the problem that Figali gave me was sort of in the context of convex cones. So it was, I was out of time here, so let me speed through this. So suppose you have an ice cream cone, okay, ice cream cone. Just shoot out rays to infinity along its boundary. Okay, so you get something like this. It goes to infinity. And suppose that it's open, so that the boundary, right, it's open. Then you can ask the question, okay, among subsets of this cone, which one minimizes the perimeter inside the cone? So you can, because the cone is open, you can glue yourself to the boundary and you don't pay any perimeter, because we just care about the perimeter inside the cone. So in 2 dimensions, if let's say this is a set, some chalk. You're just counting this perimeter. It's just the perimeter inside the cone, right? So that, I mean, you want to glue yourself to the boundary as much as possible because you don't pay anything for perimeter, right? If you're, I mean, if you want to optimize. So, so can you sort of guess which set would probably be the optimal guy? Just think in 2 dimensions.
A circle?
Yeah, just a circle, right? So you want a circle intersected, let's say this is the origin, you just want, so you fix a volume, right? Fix your favorite number, let's say 1, and look at all subsets of the cone with area equal 1, and ask, okay, which one minimizes the perimeter inside the cone? But in some sense, you just, R theta is like the best you can do, right? Because, I mean, you just squish everything downstairs, use the fact that it's an open cone, you don't pay anything for the sides, you just pay a little bit R theta for, the arc. I mean, you can't do better than that, right? I mean, in some sense, so, but this was kind of like a very hard sort of problem. And in 91, this was done in generality in 91. So, I mean, in like 2-dimensional cases and stuff, I think we've had that since the 20s. But in 91, this was done in generality, and that's the way it looks. So the optimal guy now is ball intersected the cone. And so sort of my problem was to understand its stability. So in a recent paper, we prove this estimate. And in the asymmetry index, remember we were taking this infimum over all possible configurations of the ball and translations. What we're doing here is there are no translations. There's not, I mean, if the measure of E is equal to the measure of K, K being the ball intersected the cone, then this is true, without translations. So basically, I mean, which makes sense, right? Because I mean, in some sense, you're able to kill a translation because, well, you already know by the previous work that up to a translation, you're at a ball intersected the cone. But come on, I mean, you can't be up here, right? I mean, this would be kind of silly because then you pay this much perimeter. So intuitively, at least in 2 dimensions, you shouldn't be too far away from the actual ball intersected the cone, not only up to translation. So, in some sense, you have to control this translation, but it's a bit tricky to do that in generality. But anyway, nevertheless, it's true, and I think that's it. So, sorry, I'm a little bit 2-3 minutes over, but.
Are there any questions? No? All right, let's thank our speaker again.